We are now going to be looking at invariant points. So I mentioned this in the first video, and this is to do with points on a shape which do not change place after a transformation. So there's various properties that apply to each of the four different types of transformations and how invariance can apply. So invariance, if you think about the word variance and variation, invariance means it doesn't vary, it doesn't change. So the first thing to remember is a point that stays in the same place after a transformation. Now we're going to look at rotations first and look at the properties of rotations as we do this. So a center of rotation is invariant if it lies on the shape. So if you're rotating a shape and the center of rotation is on the shape, then it's not going to move. So for example, just take a moment to look at this shape here. If we are rotating this 180 degrees, about 3, 3, so there's the red, that red dot is the center of rotation. Once we rotate the shape, that point hasn't changed place in the original shape, in the original object and the image, or the original shape and the transform shape. So we can say the point 3, 3 is invariant because it hasn't moved. So let's look at a second example here. If we're doing the same grey shape and we're rotating it about 0.44, so 44 is this green point here, you can see once you've done your rotation, that green shape, there is no points on the original shape that have not moved. The whole shape has moved. So we can say there are no invariant points. So this general rule applies to all types of rotations. If the center of rotation is on the shape, that point is invariant, and you might be required to describe that invariance by pointing out the coordinates of that invariant point. Okay, so another example here. Describe the invariant point for each rotation in this case. So have a go with both of these questions first, and then I'm going to go through them. Pause the video. Okay, so you should have had a go with this. So if you rotate this shape around the point 3, 2, you can see automatically it's not going to have any points of invariance because the whole shape is going to be in a different place. For this question B, rotating about 3, 2, well, this time that invariant, the center of rotation is inside the shape. So we can see if that's where you're going to rotate the shape. Once you rotate it, that point hasn't moved. So because it hasn't moved, 0.32 is invariant. So that's rotations. What we're going to look at now is reflections. What are the properties of shapes when we're reflecting? So any points on the shape that are on the mirror line itself are invariant. So let's look at this example here. So we have a 1, 2, 3, 4, so it's irregular pentagon there. Describe the invariant points when the shape is reflected in the line y equals 3. So we're going to draw the line y equals 3 first of all. So that's our mirror line. And then once you've drawn your reflected shape, you can see that this point here, 1, 3 and 4, 3, they haven't actually moved and they stay in the same place, or in other words, they are invariant. So there's two invariant points in this case. So anything on the mirror line is invariant when you're looking at reflections. Here's a second example here. So any points on the shape that are on the mirror line is invariant, so we already know that. And what we want to do is just reflect this shape on the mirror line there. Now what you can see is actually there's a whole range of values there that are reflected on there that are invariant, that don't actually move. So what we can see is that's your reflection, your image, and we can see all of the points from 2, 4 down to 2, 2. Now we have to be careful with coordinates because you're usually used to using whole numbers. So for example, this coordinate is 2, 2, that's 2, 3, and 2, 4. In theory, we do have, the line is, actually we can use decimals and fractions. We can have 2.5 to 2.5 to 3.5. We can go, there's an infinite number of points here. So what we can say is, we have to be careful with the language, all of the points on the line segment from 2, 2 to 2, 4 are invariant. So how many points are there on the line? Like I said, there's an infinite number of points. It's not just a case of 3 coordinates, which some people might assume, or just 2 at the end. It's actually going to be an infinite number of them. So that's reflections. Here's an example for you to try and see if you can figure out. Okay, so hopefully you tried this out and you tried to draw the reflection. Now if you have the equation y equals x as your mirror line, and then you've done your reflection of your shape, what you can see is those points on that line have stayed exactly where they are. So again, we'll highlight it with a pink diagonal. And what we can say is all of the points on the line segment from 3, 3 to 4, 4 are invariant. We must say all of the points on the line segment rather than points 3, 3 and 4, 4. It's not just 2 coordinates. Okay, translations. This one's going to be perhaps a little bit easier than the other two. If you're looking at translations, there's no invariant points. So if you imagine you're translating this shape, you're moving it 1 unit to the right and 2 units down, well, you can see none of the points stay where they are. There are no invariant points with translations. So that's your translation. Now 0, 0 doesn't really count as a translation because you haven't actually translated the shape. It's just the original shape. Okay, so enlargements. The center of enlargement is an invariant point if it lies on the shape. So it's kind of similar to center of rotation. In this case, the center of enlargement is invariant if it's on the shape. So for example, describe the invariant points when the shape is enlarged by a scale factor 2. So there is our center. So we're looking at 2, 1. There's our center of enlargement. When you enlarge the shape about that point, if you look at the ratios, that point there is, if you look at the length of the pink shape, you've got a length of 6, and the original shape has a length of 3. So 1/3 of the way along is that point, and it's actually 1/3 of the way along for both shapes, ends up at 2, 1. So actually that point hasn't changed. We can say that 2, 1 is invariant. Another example. So again, if it lies on the shape, it's going to be invariant. So have a go with this, pause the video. So describe the invariant points. Enlarging by scale factor 3 with center 0, 1. So that is your enlargement, and we can see there are no invariant points here. So there is going to be a summary sheet on this, on the invariant points. This summary sheet should be quite useful just as a kind of overview of all of the different aspects of transformations. I'll share that with you guys on the classroom. So make sure to hit subscribe, smash the like button, and I'll see you for the next topic.